There you go. Let me get the camera set up. Yeah.
I'll move this closer. Is it showing up?
I got you. Sorry, I didn't have time to respond, but sure, yeah. No problem. For the future, should we just start sticking to only one of them, like Screencast? Okay.
Yeah.
Can we do like an in-class vote?
Yeah, let's do that.
All right.
Well, we'll have to see how many.
No, only the people who show up get to vote.
No, I mean how many people have actually watched both.
I'll actually watch both. Okay.
Or
Just
watch.
which one would you watch?
Yeah. Okay.
All right. So just a quick vote. Which one would you rather watch? Well, okay. Most of you haven't watched both, but if you were to watch one, which one would it be? The screencast or the video? So screencast. Video.
It's 2v2. All right, who's gonna be the third person to tie break?
All right, because it's just kind of annoying to have to set up both.
Well, I'll just switch to video.
Well, I'll just switch to video.
To resolve the tiebreaker.
Oh, there we go. There we
Okay,
go.
for today, I'll still have both.
Alright. The slides should be posted to the website now. Yeah.
Can you add can you add a value in a specific? Let's assume you have a map of like some keys to some vector of values.
Yes.
And then can you add values to that specific vector for that specific key? And how do you access that vector?
This is me after class.
Okay.
I will definitely answer. But
Thank you
yes,
so much.
that's a great question. Okay. Whew. All right. Since the screencast is going, is it okay if I start, Avery? All right. Well, welcome everyone. Welcome to the end of week 3. Congrats on making it here so far. So today we're going to be finishing up containers, adapters, and iterators from the STL and covering a couple of cool use cases. And then over the next 2 lectures, we'll be covering templates and algorithms. And those are really where you'll see what you'll end up using in interview problems, for example, things like that. So we'll be wrapping up the STL, but you'll get to see lots of cool things before we end. So game plan for today, finish a couple of things from last time and then cover sort of the end of our containers unit. So before we jump into the thread that we start at the end of class, iterators, one thing we wanted to do, we mentioned earlier that among the associative containers, we have maps and sets, unordered maps and unordered sets. But in fact, and one of the unifying themes of all of those was that they could only ever take one instance of any particular value. So if you tried to add the same value again, it would just overwrite what was there before. But we gave you a little bit of foreshadowing that, in fact, if you want it, C++ also has another data structure that allows you to add the same key with different values multiple times in a map or set, or in a map in this case. So these are called multimaps. Not very complicated, so we're going to keep them short. In general, as we said, maps, the regular map stores unique keys, but when we do want to have the same key have different values, we have this data structure called a multimap. And so the things for you guys to know is that there is no longer the bracket notation, because if you tried to access the multimap based on some key, it wouldn't know which value to return, so that makes sense to all of us. And instead of calling map bracket equals value, or map.add key equals value, we have this function called insert, which takes in a pair of the key and value that you want to insert into the map. And again, all of this comes from the fact that we can now have duplicate keys, so we need some way of distinguishing between them. So that's a brief thing on multimaps. It's more just to give you guys the idea that multimaps are out there, so if you have some sort of application where you do want the same key to have multiple values and appear multiple times, you know C++ has got your back. All right. Okay, so what we're going to do now, a brief recap of the end of class last time, because we got sort of rushed through iterators, and there are a couple concepts I want to emphasize from that again. So one more time, as a refresher, associative containers are containers that associate some key with some value. You guys are actually already familiar with these despite the different name. These are actually really just maps and sets that you've seen in 106B or 106X. And you can remember the two differences between these. All right, so iterators. Iterators we saw last time have a couple of different syntax that's associated with them. There's 4 common functions that you can do with iterators. The first one is creating an iterator, something like some container iterator type equals the container.begin, and that returns essentially you can think of as a pointer, or sorry, a finger to the very first element in that set, however first is defined. The next operation that we use with iterators is dereferencing. So to do, we use the star and then the name of the iterator notation to either retrieve the value that's already at the iterator or to set the value at that iterator if we want to. And again, this is all sort of, this is syntax review from last time. Definitely speak up if you're confused on what any of these 4 functions do. Yeah, question mark.
So my section leader for 106B said, told me about like auto iterators.
Yeah.
And he told me not to use them because it makes it difficult for debugging. And I was wondering if you could possibly explain why, and if there are contexts where you would want to use an auto iterator.
Yeah. So wait, remind me of your name one more time.
Isaac.
So Isaac just asked, you may have heard of something called auto iterator, where instead of having this super long type of std set int iterator, you just write auto and then the name of the iterator, which in this case is iter. So actually auto is a keyword that Avery briefly touched on in one of the earlier lectures, but that I believe he'll be going into more detail in one of the next couple lectures. So auto isn't actually a new type. What auto is it's a keyword that C++ came up with so that we as programmers no longer have to remember these really long, complicated types when the compiler can actually figure out that type for us. So it's actually purely a style thing. It has no impact on functionality, with some caveats here and there. So as to the question of when you want to use auto versus when you want to explicitly state the style, people will go on back and forth about this. In general, for your 106B and X classes, you don't want to use auto, mainly because it does make it harder for, say, a section leader to read your code and understand what's going on, especially if there's some sort of like logical error behind it. But in this class, and as you go out into the real world and do C++ programming, you'll find that auto is used a lot, especially when it comes to iterators because their type is super long. A good style rule is use auto whenever the type is obvious. So in this case, we know that this set is of type set int, And so if we create an iterator from it using myset.begin, it's sort of clear to us that, okay, it's an iterator of type setInt. But say if like you sort of get really complicated code and then start using auto everywhere, then it might be a little more difficult. There's one other case where we have to use auto actually, which is with something called functors. Avery will definitely be covering those. Those are similar to lambdas, if you guys have heard of those in any other programming language. But in that case, actually auto is the only possible type to use with those. But yeah, Avery will definitely cover those. That's a great question though, Isaac. Yeah. Yeah, one more question and then I'll move on.
The object we want to iterate is an unordered object, like unordered map. Can we still do it?
Oh, wait, say that one more time.
If it's an unordered map, can we still do it class?
Yeah, if it's an auto map, is what you said?
Unordered.
Or an older map.
Unordered.
An unordered map. Sorry, thank you guys. That was a great class participation for me. Okay, yeah, no, that's a great question. Yeah, so the question was, can we use iterators on unordered maps? Because in that case, it seems like, the container isn't sorted, so how would we be able to iterate through it in any way? It turns out that's exactly the use cases for iterators. Iterators, the key takeaway for you guys to have from iterators is that iterators provide a guaranteed interface. So what iterators do is they allow us to abstract away no matter what type of container it is and allow us to go through them element by element as though there were some underlying order, even though in the case of an unordered map, it may seem just like it's a really random order. So yeah, I'll say that again on the next slide, but the answer is yes, you can absolutely use iterators over unordered maps. Iterators can be used over any container because it's this abstraction away from the container. Yeah, that's a great question. And if we have more similar questions, I'll ask for questions again at the end of this recap, so hold them for now. Third function, advancing the iterator. This moves the iterator along by 1 in our in our collection of elements. And then finally, the last thing you guys will often do with iterators is compare them against the very myset.end, which will let you know whether you've reached the end of this collection of elements. So again, this is like a nice reference slide for syntax using iterators. In terms of philosophy, so that was sort of like the the functional part of iterators. The philosophical part of iterators that I want you guys to take away from this is to imagine this. So going back to your question, imagine that this is some container, any of the containers we've learned about, a vector, a deck, a stack, a unordered map, a multimap. This is whatever data structure we're using to contain our data. Of any type of container. What iterators do is allow us to go through that data structure element by element, no matter how that container is implemented under the hood. And so the really cool thing about this is that we take for granted this idea that you can have some sort of set of numbers and somehow be able to go through them one by one without repeating any of them twice, and have them come out in some sort of logical order. The reason why we can do that is because iterators provide that interface for us. So I'll leave it at that. And if we have more questions, definitely ask them. But before that, one of the practical results of iterators is that it allows us to use the exact same code to perform the same logical action, again, regardless of the data structure. So for example, let's say that we want to count the number of times an element appears in a container. One function that we might write using iterators looks like this. So you can see some of the things that we just covered syntax-wise. We have some vector of ints, which is our container in this case. We get a finger to the very start of the vector using container.begin. And then while we haven't reached the end of the container, we are plussing the iterator. And at each step, checking whether it equals the element. So this looks like a really nice, okay, that makes a lot of sense. Say we wanted to do it for a list. Notice that the only thing that changes between all three of these functions is just the type of container. The logic using the iterators doesn't change at all. And that's kind of crazy, because if you think back to like your 106B and X data types, you'll remember that, say like a vector, to implement like finding an element in a vector feels like a totally separate process than finding an element in a set or in a list or even in a well, I guess it's not possible in a stack. But what iterators, again, allow us to do is to use the exact same logical code independent of the container. So yeah, I hope one of those explanations maybe made this make more sense. And one last thing is that this might still seem impractical to you. Like it might seem to you like, oh, okay, like so it seems like the logical code is the same. So great, that means that I don't have to change the code. I can just copy the code for each type of data structure. But that still means I have to write 3 separate functions: one for a list, one for a vector, and one for a set. So it doesn't seem that much more useful. However, because we have this generalized interface, what you'll see next lecture with Avery is something called templates, which means that we can actually take all 3 of these functions and make it one single function that we call in all 3 of these cases. So you'll learn more about that, but that's just to give you a taste of like why iterators are such a core part of C++, is they allow us to generalize away the logical parts from the underlying containers. Yes, all the way in the back. That's a great question. So you notice in the for loop that all I have is just iterator equals. So this is actually a minor thing about for loop syntax. What you guys have learned a lot is that in a for loop, the very first part is the initialization. The second part is the condition that you check. And then the third part is sort of like the incrementer. Actually, what a lot of people don't tell you is that these 3 things can be manipulated just as you would any other way. So this is actually valid syntax. What's happening here is that we are initializing this iter variable in the line above. And then we are declaring the iter variable in the line above, and then initializing it within the for loop. And that's perfectly valid. Yeah, so feel free to use that in your 1 to 6b and x assignments in the front.
So a few quick questions. Is this how like .contains is implemented?
Yeah, so the question is this how .contains is implemented? Absolutely. And I don't even have to ask you for which data structure you're asking about because it's true about all of them.
Okay.
Yeah, and there's a couple different ways, but this is one possible way.
Okay.
Yeah, all the way in the back.
So asterisk iterator, that returns the index of the iterator? Or
Great
that
question.
point to, or the value there?
That's a great question. So asterisk iterator returns the value that the iterator points to. Yeah, so you can think about it like if you go back to last lecture's slide and go back through the animations one more time with the finger, that'll make it a little more clear. That's a great question. Yeah, Isaac.
I know we went over this a little bit already, but could you talk a little bit about what the colon syntax is doing in this case and what it kind of means more generally?
Yeah, so the question, oh yeah.
That's it, yeah.
Perfect. Yeah, so the question was about this colon syntax in between set int and iterator. So this is actually a question that's funny. We were just talking about this before lecture. So this has to do with the idea of namespaces, which we vaguely brought up and which you've seen before in the case of std. So one place that you've seen these 2 colons before is in something like std : vector or std : end l. So all of those are actually just namespaces. And I don't actually want to get into namespaces today, but that's a really good question. I believe we are at least touching upon them in a later lecture, and if not, come talk to us after class. Yeah, but that is a great thing to notice.
I'll just briefly add on to that. It's essentially saying that because the iterator type appears in many different namespaces for different containers, we're saying that this is the iterator for the set.
Yeah.
So, yeah. And then I also want to build on the question that someone in the back asked, which was we don't get the index for a vector using the asterisk. Then how would you actually get the index? Yeah. So there is a function in the std library called distance, and you can say distance of your current iterator against the begin iterator.
Yeah.
Yeah, so that basically tells you how many times do you move forward from begin to get to the actual function itself.
Exactly.
Yeah.
One more question, then we're going to move on.
What you just mentioned only work for containers with continuous memory, or does that work for like the
Yeah, so it would work for any container that that function is essentially basically looks at begin and it figures out how many times it has to increment until it gets to your current iterator.
Which is actually a very good distinction because it is slightly different than the index of a container. So index really only has meaning for sequence containers when it is in contiguous memory. So distance returns the distance from the begin iterator, which for sequence containers is the same as the index. For like associative containers, it just doesn't have a corollary. Good question. All right, yeah, good questions, you guys. We will continue building off of this. So if you have more questions, feel free to ask. And if worst comes to worst, I'll just punt them towards the end. But yeah, great questions. Okay, so one other thing we wanted to cover with iterators was this concept of map iterators. So map iterators are slightly different than the other iterators that we've seen because maps contain both keys and values. And so if you look at the C++ documentation online, you'll find that the iterator type in the map class is actually an iterator of type pair, string and int. Well, pair of whatever the two types are of your map. So again, this is just for knowledge in case you look online and are confused. A quick note about the pair class. So a pair, if you guys have seen this, is just two objects bundled together. It comes with this sort of syntax. It might look vaguely familiar. You can think about it almost like a struct, but in this case it comes in class form. So it's a pair, first type, second type, and then you can access each of the two elements using the name of the pair dot first and the name of the pair dot second. Awesome. And as a side note, I was trying to find Stanford's phone number, and when I searched it, it said Stanford University's phone number was this. I'm really curious what this phone number connects to. It seems weird that the university has a single phone number. But anyways, don't necessarily call now. Call after class. Yeah, so other pair syntax things, if you want to create a pair, there's a couple different ways you can do so. The top is using the uniform initializer that Avery talked about. The second one is a function that C++ has defined for us. And then the third one isn't really doing anything. This is actually creating a pair and then immediately throwing it away because we're not using it anyway. But this is all just reference for you guys. If you see pair, and also a pair may or may not be useful on assignment 1. You don't have to use a pair, but it's one possible option. Awesome. So to apply the pair iterator, to apply the pair class back to map iterators, just for a couple of the differences between map iterators and the iterators that we already saw, almost everything is the same. You still retrieve the map iterator using m.begin, and you still compare it to m.end to tell when you've reached the end of the map. The sole difference is that when you are accessing it using the asterisk function, it's not enough to just say asterisk, the name of the iterator. You now have to say asterisk, the name of the iterator, parentheses, dot, and then either first or second. And first will return the key, second will return the value. Yes?
Sorry,
Brian,
I
go
still
for it.
don't understand like why you use plus I instead of I plus plus.
Yeah, okay, so plus I versus I plus plus, this goes back to the idea of it's the post or prefix incrementer. Yes, okay. Essentially the idea is just, so what I'll say for heuristics is that when this is on a line by itself, the two are exactly identical. The one case that's different is when you say something like int I equals plus I. What the plus means is it means at what point during the execution of that line do you add 1. If it comes before, that means that you add 1 before executing the line. So if you say int I equals int integer equals plus 1, that means add 1 and then assign it to the variable integer. If the plus comes afterwards, that means assign I to the variable integer and then add 1 to the variable I.
So in
Yeah.
this case, it doesn't matter.
In this case, it doesn't matter because it's on a single line by itself.
Yeah,
Exactly.
I'll point out some really pedantic people say that plus I. If you're using it on its own, technically plus I is very
Slightly
slightly
better.
faster than
Yeah.
I plus. It's like one assembly faster.
Exactly.
So no one actually cares, but if you want to like annoy your section or something, you can point it out.
Yeah, and that's why we sort of also default to plus before. Yeah, one question.
Can we say that the iterators are basically like a type of pointer?
Great question. So we actually had a similar question last lecture. So are iterators, and this is actually a great question because I wanted to clarify this. Are iterators a type of pointer? We will actually get to that at the end of lecture today. As a preview, it's the other way around. A pointer is a type of iterator. But yeah, that's a preview. We'll be talking about iterator types at the end of lecture today. One important thing to note, when you are accessing a thing like a pair, you must have these parentheses around the dereference I, because otherwise if you don't, the order of operations will actually say that I.first is first evaluated, and then you dereference the whole I.first. So in case you get, that's a common bug that you might see, you'll want to use parentheses. You might also see another syntax called I arrow first. Yeah, but if that doesn't sound familiar to you, then ignore it. This is perfectly fine.
Is it on the next slide?
It is not.
Oh.
All right. Okay, so let's dive into further iterator usages. So up to this point, what we've seen with iterators, and I guess what I've said probably 10 times, is that we can use them to iterate across a collection of elements. It turns out iterators can also be used, and in fact are mostly used for a lot of other really useful things, which we will see right now. Yes. So let's hop over to Qt Creator. All right, so I am going to actually, nope, Mac. We will do this the long way. All right. So there's a couple different things we can use now that we know that iterators exist. So for example, let's say we have a vector and we want to sort the vector of elements. So I've already written like a print vector function up there. So what we can do is let's say before sort, and then let's print our vector. And then so there's I guess this is just a preview of what you guys will see later in the algorithms lecture, 2 lectures from now. But these are some of the most common algorithms that you'll find that use iterators. So for example, we've included this library include algorithm up at the top, and this has a lot of the algorithms that you'll see. In this case, it has an algorithm called stdsort. And again, you can see on the right sort of the different possible options for sort. And what we'll use in this case is that second one. So all we need to do to sort this vector is just pass in vector.begin and vector.end. And then we can see out after sort. All right, and then let's see what happens. This is a Qt Creator error, and actually this is the reason why Avery doesn't use Qt Creator in lectures, because this error happens. But it's okay if you get that error, you just run it again as common. There we go. So as you've seen, we started off with a super random vector. I have no idea where those numbers came from. And then after that, it's all in sorted order. So just an example of some of the things you can do with iterators. There's a couple other ones that I want to show you today. And in fact, let me double check that I'm not forgetting any of them. So one other really common one is the idea of finding an element in a vector. So you remember from lecture last time that we actually saw a way to do that. We saw a way to do the equivalent of the Stanford contains key function. Does anyone remember what function we used to do the equivalent of contains key? What? Say that louder. Yeah, that's a good answer. So .contains is actually a new C++ 20 feature that'll be coming out, but does the exact same thing. Does anyone remember what old C++ feature we used to do it? Yeah, right there. Count. Exactly, yeah, count. Can you explain how we use count to determine whether there's an element?
It returns 0 or 1.
Exactly. So count returns how many times it appears. So if it's 1, it's in there. Can someone tell me, now that we know that multimaps exist, what are the possible values of count in a multimap? Quick check of understanding. Hey, exactly. Trick question. It's actually anything above 0. 0 and above. Yeah. So no longer limited to 0 or 1. But perfect. So what we're going to do right now is actually do another way of determining whether there's an element in a vector. And in fact, this way is actually slightly faster than count even. Really marginally. And in fact, after C++ 20 comes out, you'll want to use .contains. But all right. So what we're going to do, let's say there's some element that we want to find. Let's check if 5 is in there. Then what we'll do is, so one other one that we can see, std.find, and we can again see what the constructor is or what parameters we need to pass. And it looks like we need to pass in the first parameter that we want to start looking from, the last parameter we want to stop looking at, and then the value we want to find. So this is going to be vec.begin again, vec.end again, and then element to find. And if we do that, we can say what find does is, and then I'm going to say, what find does is it returns an iterator that points to either where the element is in that container or to vec.end if it's not in the container. So we'll be checking exactly that. If iterator equals vec.end, then cout not found, else cout all right, and let's check if that works. And so and that was exactly what we expected. Again, showing these in action. And the reason why, actually, that using this way of determining whether something is in a container versus using the count way is faster is if you look at the implementation of C++ libraries, you'll see that the .count function is actually implemented using find. So find is faster because it actually just saves you one function. Yeah, in the back.
So you didn't have to declare an iterator variable or anything like that for sort?
Great question. Yeah, so why didn't we have to do any sort of declare any sort of iterator variable for sort? So in sort's case, there isn't actually an iterator that we want to work with. So in the case of the sort function, what we want to do is we want to give it some sort of underlying container and have it sort that container for us. There's no sort of like finger that we want to retrieve from that afterwards. So that's why. So sort is actually implemented without any sort of return value. Yeah, question?
If the element to be found is the last element, would it print not found because you're checking?
That's actually a great question. So the question was, what if the element to find is actually the last element? Wouldn't that compare equal to vec.end? And so you would print not found? So that's actually a very important clarification. Vec.end actually doesn't point to the last element. What it points to is sort of the element past the last element. So the first non-existent thing. So that's a great question. In this case, it will not compare to vec.end, and so it'll be successful. Great clarification, thank you. Yeah, any other questions so far? No, all right. So there is one more that we want to do. So the last one, let's say we have some sort of set of integers. We can call it my set, and then let's do like 1, 3, 57, 137. All right. One other really useful function using iterators is the fact that you can iterate over a range of elements in any sort of collection. So in this case, the functions that we're going to use are, I'm going to use auto again, just so you can see this in practice. So again, set int has a type iterator. Let's call that iter. And the function that we're going to use is called lower bound. And we can see it takes a first, a last, and a value to find. It turns out that lower bound will default to .begin and .end. And so what we can do, so it turns out you can call it on a particular container to have it automatically default to begin and end, and so we can just pass in some value. Let's pass in 2. Oops, that was not 2. And so what lower bound does is it finds the very first element that is greater than the element that you passed in, than the value that you passed in. So in this case, we would expect it to return a finger to the element 3. And then let's find one more. What upper bound does is it actually does, the name is sort of misleading, it actually does exactly the same thing as lower bound, except if the value is equal to the element, it will also return that. So if we say upper bound 57, it will return 57, whereas if we had said lower bound 57, it would have returned 137. Does that make sense? Or rather, it would turn a finger pointing to those, not the exact number. Okay, so then this is to give one more time an example of how it looks like to loop over loop over using iterators and to demonstrate that we don't have to start at vec.begin and vec.end. In this case, now that we have this nice iter pointing to the beginning of our range and end pointing to the end of our range, we can say while iter doesn't equal end, then we can see out, and then to get the value that the finger is pointing at, we use the asterisk, see out iter and L, and then we need a plus plus iter. So let's try that and see what happens. Perfect, and that's exactly what we expected. Awesome. So before we move on, does anyone have any questions from those 3 examples? Yeah. Yeah, all the way in the back.
So lower bound, would that be inclusive? So if you had done it with 3, would it still print 3?
That's a great question. So lower bound is not inclusive. Yeah, it's almost kind of misleading. So lower bound means the element strictly greater than the value, or the first element strictly, the smallest element strictly greater than the value. And upper bound is the smallest element greater than or equal to value. Yeah, good question. Any other questions? Yeah. And again, this is the sort of stuff that you can wow a recruiter with, because a lot of recruiters honestly don't even know, aren't familiar with C++ algorithms. So very cool. Yeah, question right there.
About the sort function, what if the elements in the vector is not in integer, like a structure that we define ourselves?
Yeah.
And can we also use the sort and define the operator like less than and greater than?
Yeah, great question. So the question was, Avery,
Oh.
yeah, so the question was, what if we have a vector of our own defined class? Like, can we still use the sort function? Do we need to define our own less than operator? And then Avery.
Yeah, so there are 2 ways you can do that. One is to define, yeah, as you said, you can define your own less than and greater than operator for that object. In which case, what sort does is it uses the less than and greater than operator for you. So, for example, if I define, let's say we had student structs, and we compared all students by, let's be mean and say GPAs, then what happens is it will sort the students by GPAs. All right. The other way to do it, which is a better way to do it, is to use these things called lambda functions. So you essentially create your own custom comparison function. We will do that next Thursday. We have I have a large example of coding. Essentially, you can sort students based on a lot of different things. And then you can use that using lambda. All right, so we'll cover that next week. That's a really good question.
Good question. So yeah, definitely possible. Yeah, right there.
What sorting methods that C++ use? Is it like the most efficient?
Great question. So what sorting method does C++ use to implement sort? I'd actually have to take a look at that. I haven't taken a look at that. That's a great question. So we'll get back to you after class.
My guess is like for small values it does like insertion sort, and then for larger values it does quick sort.
Yeah, it most likely.
For all values?
No, for larger values.
For larger values, yeah.
Yeah.
Yeah. Yeah.
Yeah, and one of the nice things about the STL in particular is that you're pretty much guaranteed that whatever implementation they chose to use is the most efficient one because it's part of the standard library. But yeah, we will get back to you on how it actually does that. Yeah, question.
What's the memory allocation that it's like given to an iterator type?
What's the memory allocation given to an iterator type?
Yeah,
Oh, yeah, great question. So an iterator essentially is just a memory address, but it has this overlying interface that makes it different than a pointer because it guarantees that you can do things, for example, like increment by 1. But like the iterator itself should just be a memory address.
Okay, so can you like overflow it or no?
What do you mean by overflow?
Like that you are giving it like a huge address that that corresponds to some physical address within your machine.
Like can you give it an address that is invalid?
Yeah.
Yes, right. Yeah. So one of the things about iterators is that because you were always requesting them from the container type, it would have had to have been a bug within the container type. whereas one of the things with pointers is that pointers are actually a relic of C, which actually has even less protection / more flexibility. Well, so C has solely unprotected, I guess, tools to use. So with pointers, for example, you can set the memory address arbitrarily. With iterators, on the other hand, you're actually never working directly with the memory addresses. You're always working in relation to some sort of container, and so because of that, you're actually safe. Yeah, great question. Awesome. So let's move on in that case. So as a brief review, you guys can go back to the slides. Once again, we now have seen 2 different ways of implementing contains key, one using count, one using find. And again, find is marginally faster. And of course, C++20 will bring its own function. So in a couple of years, you guys will be using a new thing. But now you can tell all your friends that you know that find is faster than count. Ranges, this was the last thing that I wanted to show you. If you want to look up ranges on your container, these are just nice metrics for how to do that. And then you can take a look at this at the end of class. But basically, if you guys haven't seen that mathematical notation before, the bracket means that it's inclusive, so including A and B. The parentheses means excluding that number. But yeah, so this is sort of a reference for you guys if you want to look at ranges over your containers. Now you know. Awesome. So one other application of iterators that you guys may have seen already. How many of you guys have heard of something that looks like this? It's like for something thing, and then either like in or colon, and then the name of the container. Like raise your hand if you've seen it. Awesome. So you guys have actually just learned how to implement that yourself. So actually, if you take a look at the implementation of, this is called a range-based for loop, or for each loop might be the more common term. It's actually implemented exactly as you guys have just seen, using iterators. So that's kind of cool. Like you will never see this sort of thing in 106B or X, but you will definitely see the for each loop above. So now you know how it works. And yeah, very cool. All right, and yeah, you can see that from the documentation. It's purely implemented using iterators. Yeah.
For each is its own thing in the STL library.
Say that one more time.
You can do like for each with like its own.
Yes. So there is also a library that is for_each that is slightly different. There's also an algorithm called for each, I believe. I'm not sure if that's the one you're referring to. Yeah, so that's slightly different. The official term in C++ for this is a range-based for loop. In something like Python, you may have heard it as like a for each loop, but yeah, there's technically also a for each function. Yeah, good clarification.
We'll talk about both on next Thursday.
Yeah, actually, perfect. Cool. So in our remaining 10 minutes, I'm going to quickly cover this because I've gotten a couple questions on it regarding assignment 1, and then I'm going to finish up with iterator types. So just if you guys have taken a look at assignment 1, you'll notice that there are 3 structs that you're working with, one called node, one called edge, and one called simple graph. This is just a brief refresher of how struct syntax works in case you're unfamiliar with that. I'm going to go through it kind of quickly and then leave it in the slides on the website so you guys can go back and reference. So yeah, remember, there's just a couple different parts if you want to declare your own struct, which you most likely won't need to do for this assignment, but that's the way to do it. I actually have a typo there. There should be a semicolon after the ending brace in that struct. To initialize a struct object, there are a couple different ways. You can either, and this goes back to the different ways of initializing that Avery mentioned. The one that we probably recommend is the uniform initializer right here, where it's struct, then the struct name, and then the name of the variable, and then in braces, the values of that struct. One thing in C++ is that you can actually sometimes omit the struct keyword. So if you don't have that and your program's still compiling, that's why it's doing so. That said, yeah. If you're curious about that, you can talk to me afterwards. And then finally, if you want to reference a element of a struct, then it uses the same dot notation that you guys have seen elsewhere. So if, say, for some hypothetical reason, we had 2 structs named simple graph and node, the way that you could theoretically push back a node onto that graph's vector of nodes would be using something like this syntax. And notice here what we're doing is we're just creating that node on the fly and immediately appending it to the graph. And that's why we don't have to store it in a variable. You don't have to do it this way. Feel free to do it any other way that compiles. But for any of you that are confused a bit on how to get started on the structure of, on the syntax of structs, yeah, I'll leave this as a reference. Cool. Any questions before I dive into iterator types? That was a lot in a short amount of time. Yeah, Manuka.
For structs, sometimes I see people using pointers to structs, like especially graphs and nodes and stuff. So why do sometimes, or when working with structs themselves, sometimes and sometimes with pointers to structs? Like what's the difference? Why do you use one or the other?
Right. So the question is that, especially within like 106, 107, and maybe 106 B or X. Although I'd be sort of surprised if they were working with pointers. But you'll see a lot of times when you're working with structs, you'll see struct something and then pointer rather than working with a struct directly. It all has to do with your application. Basically, if you are trying to work with, actually this might be a sort of complicated question going back more to like when do you want to use a pointer to an object versus the object itself. So come talk to me afterwards and we'll go over that. And if anyone else is interested, we'll have like a short discussion outside of class.
Yeah,
Good question though.
We'll probably cover this when we talk about inheritance, because there are some issues with inheritance regarding pointers versus the actual struct itself.
Perfect. Yeah. So we'll also get into that. Awesome. Cool. Okay. So iterator types. So so far, I've actually almost not quite lied to you, but sort of oversimplified things a bit. So far, the only thing that we've done with the iterators that we've had is incremented them. We've only used like iterator plus plus or plus plus iterator. But it seems like to us, just intuitively, there should be some way of being able to do something like iterator plus 3 or something like that for say a vector or a deck, or like an iterator minus 1. Like just based on an experience working with vectors or decks, it seems like that should be something we can do, like move the finger around arbitrarily. That said, what if we had a data structure called a list? So no worries if you haven't seen a list before. People in 106B and X, you will see this in a couple of weeks. For those who have seen this is the same as a linked list. And with those, the way that these work is that instead of having like an array of contiguous memory that we're working with, to traverse a list, what you have to do is you have to start at the very head of the list and then read where to go next in the list. So the only way to traverse a list is by reading from each node to each node. So with something like this, then in this case, it seems weird to think about something like, I have a finger and I can arbitrarily jump to the third one, because how would I know where the third one is without going through each of the ones in order? And our intuition is exactly correct. We do want something that acts like this for vectors and decks, but we also know that we can't have something like that for lists. So how do we get around that using iterators? So, yes, and you can actually see that this is the case if you try this out in Qt Creator. If you try to do something like list.begin plus 3, it'll throw a syntax error. If you try to do the same thing with a vector, it'll work perfectly fine. Okay, so what C++ has done to resolve this problem, inherently the problem here is that there are some containers have slightly different requirements than other containers, but yet we have said that iterators are supposed to be this like generalized interface that can work with anything. It turns out both of those are still true. The compromise that we've come to is that we've instead defined 5 different types of iterators. Each of these types of iterators is still an interface. It's still just a set of promises that it's making about what it can do. The difference is that some of them are more powerful than others. Some of them have more functionality they can do than others. And we will actually get into these right now. You'll see this at the bottom, and it'll start to make sense as we go through the 5 types. So first off, I do want to say that all 4 things that we covered at the beginning of lecture of what we said an iterator could do are true for all 5 of these types. So these 4 basic functions, dereferencing, incrementing by 1, and creating iterators, all of these are still valid. The difference is that some of these have additional functionality that others don't have. So our first type is an input iterator. These are for sequential single pass data structures, and additionally have the functionality that they're read-only. Okay, so what does this all mean? Let's say that we have something, like what we just saw with find or count. What single pass means is that it only requires a single iteration over all of the elements to figure out what we want to do. So for example, in the case of count, we only have to go through each element once to be able to count how many elements are in that container. And same thing with find. And the other key component of this is that to implement these functions, the only thing we have to do is read the value from that iterator. We don't have to write any new values. So these types of input iterators, as you can see, this is from the C++ documentation. These types of iterators are called input iterators. And so we've actually already seen these, as we just saw with find and count, and also with what you guys saw back in lecture 1 or 2 with input streams. So input streams work exactly the same way. The iterators can only move forward, and they can only increment by 1, and they are only read-only. Okay, that was a lot of constraints. Any questions so far? Okay, cool. So that's input iterators. Output iterators are going to be very similar. Again, they only work for sequential, single-pass things that you want to do. The difference is that instead of read-only, these are write-only. So it is impossible to do something like int I equals dereference iter. In this case, you can only ever set iter to be a value. And right now, it seems sort of awkward, like, why would I ever want to do that? Once again, there are actually surprising use cases for this. One of these is output streams, so cout. You are always writing, you are never reading from cout. The other one is a function called copy, which is also in the algorithms library, where you are copying from one, where you can see you're using an input iterator to read from the first containers and an output iterator to write to your new container. So this is an example of how these iterator types work together. Two more minutes. All right. Forward iterators, the exact same thing as input and output iterators, except, sorry, let me rephrase that. You can think of forward iterators as being both an input and output iterator at the same time, meaning that they can both read and write, with one additional thing being that it can make multiple passes as opposed to a single pass. Question you might ask is, why would I make multiple passes? You can imagine some sort of function like replace, where you want to look through your container for certain elements and replace them based on a condition. Another thing that you might see forward iterators from is from, if you guys recall, from the sequence containers unit, I said that there were 5 types of sequence containers: vector, dec, and then list, forward list, and one more that I'm forgetting off the top of my head. You don't need to know what this is, but for those of you who are familiar with the idea of singly linked list, you can think of that as a singly linked list. Bi-directional iterator, same as a forward iterator, except you can also decrement. So you'll notice up to this point, we have never been able to do something like iterator minus minus. It turns out this is only possible with bi-directional and random access iterators. And a case where you might see a bi-directional iterator, the function reverse, where you want to take a collection and reverse all of the elements, then of course you want to be able to move back and forth. Maps and sets are actually also implemented using bidirectional iterators. You can decrement your iterator, you can move forward, but you'll see soon why they aren't random iterators, which is our very last type of iterators, which is random access iterators are the most powerful type of iterators. And this is where I finally answer your question. When people think about pointers, they are thinking about a type of random access iterator. So you can think about it as random access iterators are the interface for what a pointer is. It promises that you can always increment, decrement, like add arbitrary numbers, subtract arbitrary numbers, read and write, everything like that. So random access is the type of iterator that people might feel most familiar with. They're the most powerful, and some examples of these are, again, with what we use every day with vectors, decs, and even strings, if we wanted to use iterators on strings. And again, there are pointers. The last note I want to make is that you'll notice that each of these has arrows to the others. That's to say that a random access iterator is a type of bidirectional iterator. Why is that? It's because a random access iterator makes all the same promises that a bidirectional iterator does and more. So that's what these arrows mean, is that each of the ones on the right is a more powerful version of the ones on the left. So, so each of these is a type of the ones on its left. All right, thank you guys. Yeah, let me, if you have any questions, we will be right outside, and have a great weekend.
We finished on time. Yay!
Yeah, we finished on time.
Wow.
I know. We're reading our feedback forms.
All right.
Cool.
Let's get this out of the way.